And I should be live now. Hey everyone, so just confirmed I am live. Welcome to my first stream. So I hope there won't be many technical problems, but let's get started. So uh, on today's agenda, I will be talking about my approach to audits, and then we'll be reviewing some smart contracts live. I asked on Twitter for people to submit some smart contracts, and I've selected some of those and created a list here. These are also mentioned in the description of the live stream. If you want to look at the source codes yourself, you can look here. If we have time, I have some extras here, but I honestly I don't think we will be able to get to the extras in this stream. Perhaps for some other day. So before getting started, just about myself. For those who don't know me, I'm a security researcher and Ethereum developer. I've been in the blockchain space for about 5 years now. And I started with Bitcoin and Monero, moved to Ethereum. Right now, I'm helping SushiSwap build their next gen AMM named Trident, and that is coming soon. So, about this stream, the target audience is basically someone who has basic understanding of Ethereum and Solidity. So, for those who are new to Ethereum or Solidity, these are some of the resources I recommend. I have this list in the description as well. The Ethereum book is basically like one of my favorite resource for the newcomers. Then we have Crypto Zombies. So this Ethereum book will give you the basics of Ethereum and some introduction to Solidity. So definitely start with this. Then if you decide to continue on with Solidity, then I think Crypto Zombies is quite fun. It is an interactive game where you can learn Solidity by completing challenges. Similarly, we have Solidity by Example. This, I believe, was inspired by Rust by Example, or at least I saw the Rust version first. But this is another great resource to learn Solidity. Once we have done the basics with these three things, then I would suggest that you go over the Solidity's docs, just like glance over each and every page of these docs. These can be a bit crude, but I can assure you that these docs have some hidden golds inside them, some gold nuggets, which are like great pieces of advice from the Solidity authors themselves. You can also look at Ethereum Org's website. They have a good collection of resources. You can pick any of the resources they have mentioned. All of them are of high quality. So once you have learned Solidity and you want to get into some security type aspects, or even if you just want to do advanced stuff, this CTF by folks from OpenZeppelin is, I think, awesome. I really like this. Go here, try these challenges if you can. This is basically a CTF where you have different challenges and you have to basically hack the smart contract to complete the challenge. And these are quite fun, and they tell you some like common vulnerabilities in the smart contracts and that you should be aware of and stuff like that. So I definitely recommend everyone to try this out, but probably best to do it after you have done the basics of Solidity. Then I think these are the resources I recommend. I will just dive into the auditing approach now. I want to cover a lot of content today, so if I'm going a bit fast, apologies for that. Actually, let me just open the comments in my mobile so that I can follow if there's anything that is being posted in the comments. Yeah, I have a very jank setup for streaming. First time doing this, so yeah. Okay, I have the comments in front of me now. So yeah, the auditing approach. I have some bullet points here that I will expand on. Let me enable word wrapping. So the approach that I take to audits, I recommend like not only auditors follow sort of this checklist or like this approach, but I think this can be helpful just for like developers as well who are trying to think of their project as like from a securities point of view and trying to fill any holes or gaps that might be present. So whenever I get a request to audit a project, the first thing I do is like whenever I'm starting an audit, the first thing I'll do is go over all the non-code resources that the developers have provided me. So this will include any documentation, white papers, marketing material, blog posts, and anything like that. So stuff that will give you an idea of what the project is meant to do. At this stage, I do not want to look at the smart contracts because I first try to create an image of what they should look like, and then I'll compare if the image matches my description. If you I feel like if you delve directly into smart contracts, then oftentimes you just focus on what the smart contract is doing and not on what the smart contract is supposed to do. So this is one thing I really like. Just follow all the known non-code resource first and then delve into the smart contract. So once I've gotten an idea of what the project is, I'll delve into the smart contract. So the first thing I do when I look at new smart contracts is to just glance over them briefly and to understand the architecture that they are using. At this point, I will not be reading every line, like every source code. If a contract says that it is an ERC20 token, for now, I'll just believe that it is a standard ERC20 token and move on. At this stage, I just want to get an overview of the architecture of the smart contract. I'll also use tools like Surya from Consensus to plot some dependency graphs and help me better understand the architecture and how the different contracts talk to each other. Once I have this brief idea of the architecture and I know where to look for something, so like if I want to see where the ERC20 source code is, at this stage I should be able to tell where that actually is in the repository. This stage is not really very important for single or small contracts because then you can like just skip this and get to the second stage or the next step basically. In the next step, I try to create a threat model for the protocol. So if let's say let's talk about SushiSwap, their DEX. In that, you will say the actors, one actor will be the liquidity provider who is providing liquidity, and the other main actor will be the user who does the swaps. So I have like two main actors, liquidity provider and person who is swapping assets. Then you can break these further into like smart contracts who are responsible for these actions, like the pool, router, and stuff like that. But in the broad overview, there are two actors. Based on that information, I'll try to think from those actors' point of view, what they will want in this protocol, what can be some like potential exploits that can be present in this protocol. I will try to list all the theoretical attack vectors, which will include your common pitfalls. So common pitfalls used to include like missing arithmetic checks in Solidity. So before Solidity 0.8, by default, Solidity did not cause a revert on overflow or something like that. So people were like, this was a common pitfall that people had a variable that can be easily overflowed or underflowed. In Solidity 0.8, all variables are by default strictly checked for overflows and underflows. So this is not as common of a pitfall, but yeah, it still is. Then I'll also compare my like threat model and the architecture that I've created to shortlist any like past exploits techniques. So past exploit techniques like reentrancy, your oracle manipulation, taking flash loans and manipulating the pool balances, stuff like this. So basically whatever has already happened in past and we have hopefully learned from those mistakes, I'll create a list of those which may be applicable to this application, and at a later date I'll verify that these vulnerabilities are not present. Okay. So increase the font a bit. Hopefully this is better. By the way, this content is also present in the description. So if the font is still too small, you can read the description. So I was at here. So yeah, at this stage, I know the threat model. I know the architecture of the smart contracts. I know the list of potential exploits that I could have thought of. Then I'll start actually reviewing the smart contracts. So whenever I start reviewing the smart contracts, the first thing I do is like search for all places where value is being transferred. So this will be like ERC20 transfers, Ether transfers. Solidity has a transfer function. Your ERC20 transferFroms, Solidity's send function, Solidity's call function, delegate call function, and self-destruct. These are the most common ways to transfer values. I will look for each and every instance of these functions in the smart contract, and then I will walk backward from that call and see like how that call is being triggered, and if this call is secure and it can't be like manipulated, or like no unauthorized people can trigger this call and stuff like that. So walking backwards is especially helpful in large code bases where you have like thousands and thousands lines of codes. There, using this trick, you can basically like review the most critical functionality within a few minutes or hours. For smaller contracts, this is not as helpful because you can in that case just do a line by line review within a similar time frame. But I still like to do the most critical reviews first before I get into the line by line review. So when I do the line by line review, I'm looking for two main things. One is your logic bug. So anything which although is not really a security concern, but is a logic bug. So the smart contract is not behaving in a way that it is supposed to. So an example of this will be, so if I read that in the white paper and everywhere, people are saying that the project should charge a 10% fee on every transfer or something like that. But now you look at the contract code and you see that the project is actually charging 25% fee rather than 10% on every transfer, or it is not charging a fee at all. So in isolation, those issues are not really a security concern. But given that we have the context from the first point that the project should have been charging 10% fee, we can conclude here that this is a bug and should be pointed out in the audit report. I know not all auditors focus on logic bugs, and honestly, logic bugs are not my priority either. But since I'm doing a line by line review anyways, I just feel like I go ahead and keep matching everything to the specs. The main advantage of doing this matching is that you then don't end up making incorrect assumptions about a project. So you might in a normal project you might see something and you might just assume that it is how it is supposed to work, but for the project you are reviewing, it might actually be a security flaw. So it always best to match resources. The second thing I check when doing the line by line review is for the list of exploits that we earlier created. So I make sure that none of those exploits are actually applicable on these smart contracts, and these contracts are secure from those. While I'm checking these smart contracts for existing exploits, I also try to brainstorm new styles of attacks or something like that. And I think that stage is what takes the longest in my audits. Um, so I usually spend like a day on every smart contract just brainstorming different ways to like attack this or something. If I set this parameter to this value, or if I follow this path of like function calling or stuff like that. So I just try to brainstorm different approaches to find a flaw in the smart contract. It is your like typical pen testing. I'm just trying to break the security. I don't know what exactly will break. I'm just like throwing mud at it and hoping that something will stick. So at this stage, I might be trying like dozens of proof of concepts, and usually only a couple of those will actually give positive results. Positive in the sense that exploits that like vulnerabilities in the smart contracts. So in well-written smart contracts, often you will not find anything from brainstorming, but in like hastily written smart contracts, you can find dozens of vulnerabilities. Honestly, the worst or best I've done is 23 critical vulnerabilities within the single project. So that sort of code basically needs to be rewritten from scratch. So yeah. Then once you have done all the brainstorming, you have found out whatever you could, then this stage is over. At this stage, almost all of your review is complete. At least the first pass is complete. But I like to do another pass from the perspective of individual actors. So in this case, if in SushiSwap's example, I said the actors are LP provider and the person who is swapping the assets. So I'll try to get into the mindset of those users and try to do what they are doing. So these will basically be, I will basically be emulating the most commonly used use case of this project. And like I will, so a liquidity provider is supposed to add liquidity, remove liquidity. I will try to do those two. I will try to call those two functions in various combinations and permutations, whatever I think makes sense. Then from the swap perspective, I will try to swap some assets, do some multi-hop swaps and stuff like that. So this just like ensures that you are actually following the path that a normal user will follow. Like oftentimes you'll find when people are testing smart contracts, especially the testers, they will try all the weird edge cases, but they will forget to try the most common use case. So this just gives you like another review. So this is like my second pass over the smart contracts, but from the perspective of the normal users, just to make sure that the normal use case works. So once I've done this pass, I will like accumulate all my findings, share these with the developers, and they will get started on any fixes. If I find anything serious before this step, then I usually just share the findings as soon as possible so that they can start working on a fix or clarify anything if I'm missing. Obviously, while I'm doing all this review, I like to maintain an open communication channel between the developers, because oftentimes you'll see something that you may not be sure about, like what this thing should do. In those cases, it is good to talk to the developers directly to know their intent. If the developers create well-written documentation before submitting the contracts, then I think the requirement for that communication like decreases a bit, but there still is best to have a direct line of communication. After all of my manual reviews, I also run some automated tools. The best tool right now, in my opinion, is Slither from Trail of Bits. I think it covers most of the resources and is free. Consensus has their mythics or mithril. One is like open source, one is their service. It is also quite good, but I personally like just prefer Slither from like personal experiences. But definitely you can also check out CD's offering. Finally, I'll glance over the test cases and the code coverage, and like add comments there if I say anything wrong. This step is just really for like the ending conclusions and stuff. Doesn't really affect my manual review. Oftentimes, like especially when I'm brainstorming approaches, I will write some test cases myself to verify my findings. Oftentimes what happens is like I've already covered a vast majority of code coverage in my like POCs and stuff. So I don't really depend on the developers test cases, but this having good test cases is a good signal that the code was written well and it was thought out nicely. And yeah, that basically concludes my auditing approach. And once I'm done with all of these things, I wait for the developers to push any fixes or do any clarifications, answer any questions. Once the fixes are ready, I do another round of review of those fixes. That second round is honestly not as comprehensive as the first round. I don't like spend much time on it, but I'll just verify that the immediate vulnerability is fixed. So if like I found only a few smaller issues, then that is fine. I can just verify them in my second review. But with some projects, I've seen cases where like I found over a dozen critical vulnerabilities, and that really requires a rewrite of the project. In that case, although I will do a short review of your fixes, I really recommend developers to just get another audit done with me or with someone else. But it is practically not possible to review a project again in a short time span when basically everything has changed in the project. So that was it. I'll take a short break and look at the chat before I start the live review process. Okay, I think we can continue with the live review, and this is going to be the most interesting aspect of the stream in my opinion. So I've briefly looked at the smart contracts, but I haven't really spent much time on these. These are the ones that I think are small enough to review in this call. These ones I feel like are a bit too large to really cover on a stream, so I've put them in extras folders. If we have time later, we can come back to these. But otherwise, let's get started. So this contract, bridge deposit, was submitted in a tweet to me. So I think this is. So I suppose this is a contract for a multi-chain bridge. People can deposit tokens here. I see the owner can withdraw the balance. The owner can also destroy the smart contract, and people can like send funds to it using the receive function. I'm just looking at the broad architecture of the smart contract right now. We have functions that like set the owner and do some config parameters which are only callable by the owner. That's all good. These like view functions I usually just ignore when I'm doing short reviews. I will look at these when I'm doing a full audit, but for short reviews, I'll just ignore the view and pure functions, especially when you are dealing with Solidity, like newer versions of Solidity. In 0.4, this view function wasn't like mandated by the smart contract, so you could just make like non-static calls to it as well. But from newer versions of Solidity, if you call a view function, Solidity will make a static call to it rather than a regular call. Although these can still be called via normal calls, but usually, like if you're calling them from Solidity, they will be called by static call. And what that means is that if this function tries to change any state, then a panic will be caused, a revert will happen, and everything in the transaction will get rolled back. So I don't really need to focus on these much. I can just assume for now that these don't modify the state. These are just helper functions. We have some modifiers and some events. So yeah, I think I have a broad idea of what this contract is trying to do. So here people deposit some funds. This just emits an event. I suppose now an off-chain application is supposed to like catch this event and do something of this data, maybe like bridge the tokens on a different blockchain or something like that. And then basically that's it to this smart contract. These functions for withdrawing and destroying, I'm not sure what their use case is. I suppose these are present for emergencies only. Now, if I had like documentation from the dev, I could have been sure what these are meant to be. But for now, I will assume that these are just for emergency usage, because like what this contract basically is doing is you are giving all your ether to this owner, and you should only do this if you trust this owner. If like to this project, I will recommend that you make this owner a multisig and a multisig with a time lock. So like no single key should have access to this, and before this like owner can execute any action, there should be a delay of at least 1 day, in my opinion, so that like people can at least know what's going on. But assuming that people are just transferring ether here without anything in return, I assume your users already trust you. I have no idea where that trust comes from, but the user here is just trusting the owner to like keep their bargain, whatever that might be. So let's also delve into these two modifiers first. Actually, let's look at all three. So is lower than max deposit just verifies that message value is lower. Is owner just verifies owner. Can receive just verifies this is true. And this ensures that the current like max balance of the contract is less than this. I will check if this variable can be modified elsewhere. This seems like an important variable. This is set in constructor that can be called only once. That's good. And it can only be called by is owner afterwards. Okay, we'll also verify that the owner variable can't be modified by anyone. Owner is set in the constructor. And after that, I think we had a set owner function. Yep. Search didn't catch this for some reason. Oh, it did. It did. So yeah, set owner function again can only be called by the owner, so the owner can transfer the ownership to anyone else. So I think this like this is as far as I'd go for this contract, because you can clearly see the contract does not give you anything in return. All of the secure, like there is nothing wrong here, as long as the owner is like reliable and trustworthy. The only point I will point out in this smart contract is before you interact with a smart contract, please make sure that the owner is someone you trust. You are essentially transferring your money to this owner in this smart contract. Okay, I'll move on to the next contract. Let me look at the comments briefly for first. So for the fuzzing approach, Saurabh, I do use fuzzing, but not for everything. So like some people, like at SushiSwap especially, we are doing formal verification with help of Satora. So their formal verifier actually also does fuzzing in case it is unable to verify something formally. So we do some fuzzing, but we don't do fuzzing for literally everything in our contracts. That I think is a bit too time consuming. Maybe like definitely I can do that while doing audits, because fuzzing a complex smart contract can take months and months of continuous fuzzing. But I do recommend people to like developers themselves to write test cases or do fuzzing themselves for the most critical functions, like we do with help of Satora at SushiSwap. And Scar, you're right. Some fixes can open up contracts to another like other vulnerabilities, and this is why I recommend people that if you are changing your smart contract heavily in a fix, then you go for a fresh audit. Your current audit basically becomes like ineligible or void at that moment. But if the fixes are small, like just changing one percentage to another, then as a reviewer, I'm usually able to track all the effects that change is doing, and I'm able to verify that it is fine. So which extensions do I use in VS Code? Let me just open it here. So I have a dark theme, auto close tag. Yeah, I used to write HTML once, although I have not used this in a while. Auto comments, auto rename tag, AWS, bracket pair colorization. I think this one actually is quite nice. C, C++, CMake, code LLDB, Rust creates a decompiler, Docker, Ethober. Shout out to Tintin, by the way, from Consensus. He has some great plugins for VS Code. Git merger, GitHub Copilot. GitHub Copilot actually saves a decent chunk of time. Like it is basically a more like advanced version of autofill. It is usually incorrect when it tries to predict long codes like this or something, but just filling out the name, like if I enter S, it will recommend me string, so even that saves a bit of time. Gitlins, Go, GraphViz. So this one is another nice plugin from Tintin. You can use this to plot the dependencies between different smart contracts. Jupyter JSON, a bunch of markdown stuff, some diff, base JSON, path intelligence. Honestly, like as you can see, I have a bunch of stuff installed. I'm not even sure if I use everything anymore, but I do have it. Prettier is also nice. Python stuff, Rust Analyzer. So another shout out to Rust Analyzer. If anyone uses Rust, this I think is much better than RLS. Like it is like a modern alternative front end to RLS, and I think it's quite great. So I have a Solidity plugin installed, and I have Solidity metrics. This is another great plugin from Tintin. This I used to like create some basic data about smart contracts. I think this highlighting also comes from this plugin, although this does not always work on all projects, especially hard hat projects, but otherwise this is I think another nice project. Actually, this Solidity visualizer, yeah, this is the one that gives you all that highlighting, this like underlining and stuff. I think the Solidity visualizer plugin does that. Another great plugin from Tintin. So basically, you should check all his plugins out. Systemd stuff, TypeScript, Viper, WebAssembly, and yeah, I think that's it. So about Timelock, first of all, about reentrancy. Reentrancy is yes, it is one of the previous attack vectors that I check in every smart contract. I'm in this contract specifically, I'm not worried about it because only the owner can actually call it. So if the owner is the owner does not need to re-enter in any way, they already have control over the funds. And this receive function is not giving anything back to the user. So again, reentrancy is not a problem here. Although there's nothing that you can re-enter with here anyway. So yeah, Timelock. So Timelock, actually, I do have a Timelock contract that I will be reviewing later today. But Timelock is just a guard on a multisig where you say that if a multisig has to execute an action, usually a multisig, but it can be anyone. If it has to execute an action, then it must submit its intent to execute an action. Like at least 1 day or 12 hours or some time period before it can actually execute this action. So that way, whoever is using that project can tell in advance that this thing is going to change in this project. So maybe they will want to exit the project or something like that. So here, although Timelock won't really help in this case because there's no way for the user to get back their money. But if there was a time lock and let's say the time lock was 1 day. Now, if the owner wanted to withdraw balance from this smart contract, they will have to create a transaction on the blockchain. And in that transaction, they have to show that they intend to call this withdraw balance function. Now everyone has 24 hours head start. They know that the owner is going to call this withdraw balance function. So if this is something malicious or if this changes their opinion about the project, they can now exit the project and the owner will only be able to call this after 24 hours have passed. So this is the ideology behind time locks. And yeah, I do have Andre's contract under review, in the to-do list today. I will go over that. So about multisigs, I don't know if this doesn't seem like this time lock function has a multisig, but from multisig, I mean in Ethereum, the multisigs are not like BTC where you can do combine signatures, aggregate signatures. In Ethereum, multisigs are implemented as smart contracts. So that means that they are just an address. They are nothing more than an address for this contract. This contract does not care if that is an end user or if it's a Gnosis multisig or something like that. It's just recommended that you set up a Gnosis multisig or some other trusted multisig and set that address as the owner here. If this was a smart contract that was live, I would have gone to the blockchain and verified that the owner is actually a smart contract and it is a legit, the owner is actually a multisig and it is a legit multisig. A multisig basically is a smart contract in Ethereum where to execute any transaction, at least n signers must approve that transaction. Usually, if it's an end user, the end user just signs a transaction in your MetaMask, in your ledger or whatever, and that action just happens on the blockchain. But in case of a multisig, usually multisigs are n of m. So there are m of n. There are n number of signers, and at least m of those signers must sign a transaction for this to execute. So if there is a 2x3 multisig, then at least 2 individual signers must sign a transaction for that to execute. This means that if one of the signer loses access to their keys or their key gets compromised, their system is compromised or something like that, the hacker will still not be able to do fraudulent transactions from that multisig. because they need control of at least two signers in this case. So this just adds another layer of security. Obviously, like in a real project, you will also want to verify that the signers are different people in reality. Someone can just create 10 different accounts in their MetaMask and set them as 10 signers. That doesn't really increase the security much. So in real projects, you do need to be careful about all of those quirks. Okay, so complex math. So I actually have learned a bit of calculus and discrete mathematics in college. So I am able to look at like most of the stuff, but when it comes to like advanced, like super advanced formulas and mathematics, I do like tell the like developers or whatever that this is beyond what I can comprehend or what I can audit, and you should like ask someone else to verify. Obviously, your like white paper and material like documentation comes handy in this case, because even if I can't verify that the math is doing what it is like intended to do, I can at least verify that the math is doing what the documentation says that it should be doing. Although like it might not make financial sense or whatever, but at least I can verify those things. So characteristics of hackable smart contracts. I don't think there are any such characteristics. Something to catch on will be like no test cases, or this might be like a bit picky, but if you see a smart contract that is not indented properly, if the code is like this, it just shows that the developer didn't really care about the code, and that can be a signal that this contract might be vulnerable, but there aren't like any real characteristics like that. Okay, I think we'll move on now. Let's get to the options. This is the smart contract from Andre. I actually looked at the earlier version of this when he originally released it. I was gonna review that on stream, but just before the stream, I noticed he updated it with this new version. I think he added NFTs and something. So let's review this live. I haven't reviewed this one yet. So again, we'll start by just looking at the broad architecture of the contract. Before that, I can give you some like context about what this contract is supposed to do. This is a liquidity mining contract. So usually when you do liquidity mining, you get rewards in like native tokens of the protocol. So on Sushi, you might get like the Sushi token as a reward. Now this Sushi token you can do anything with, like you can stake it, you can sell it, you can do anything with that. This alternative approach says that instead of giving the token directly, you give a call option to the user. So what a call option means is that there is a fixed price set of the Sushi token, so of the token. So let's take example, let's call our token chat token. So let's say this chat token has an option which has a strike price or base price of $10. This implies that before the expiry of this option, you can like at any moment exercise this option and buy the promised chat token for $10. Doesn't matter what the price of chat token is at that point. If the chat token is trading for $5 in the open market, you will still have to pay $10 if you want to exercise this option. Again, you are free to not exercise this option. If the strike price is higher than the market, then obviously it makes sense that you just forget about this option and buy the token from the market if you want. But the interesting case is when the option is in the money. So when the price of this chat token in the market is actually higher than $10, so this chat token might be trading at $20 in like after some time. So now you see you have an option pending of chat token $10, but it is actually trading at $20 in the market. So you have a good arbitrage opportunity now. you can exercise your option, buy the chat tokens for $10 and then sell those chat tokens for $20. Or you can hold those chat tokens if you want. But at the end of the day, you are buying chat tokens at a discount by exercising your call option. This is helpful for liquidity mining because this just gives a base value to your token. If you are giving rewards in your chat token and you price the call option at $10, this sort of gives the token a base value of $10. People will not really exercise this option and then dump it for less than $10 because it will cost them $10 to exercise this option. So either people will just not exercise this option, which means there is not much sell pressure in the market from these rewards, or the price of chat token is higher than $10, which was your base price, and people will now be exercising these options and doing taking the arbitrage opportunity or holding the token or whatever. In that case, you don't really mind because the price of your token is already above what you want or what you expect or whatever. So this just gives you that protection and stops your token from dwindling down in some sense. Or just a disclaimer, I'm not an expert in finance or markets. This is just what I understand from my understanding. I might be wrong, so feel free to correct me in the chat. And this is not any financial advice or anything. These are just for educational purposes and whatever I understand from these things. So yeah, here Andre tweeted this out, just explaining what the contract does. Let's move on to the contract itself. We see an ERC 721. This is a common standard for representing NFTs. And this is just an interface, so we'll move on. Okay, this is another ERC which helps other contracts know what interface that this smart contract supports. In practice, this didn't really pick up much steam. Very few contracts implement this, but there's no problem in implementing this if Andre wants. This is a library that I will just ignore for now. I'm not sure if any of these functions are actually used. If we see a use later, we'll come back here. Same with this library. ERC 721. This is the implementation of the contract. So if I was doing a full audit, I will at least verify that, I will at least verify the basics of this implementation, that this is doing what a token is supposed to do. But since we are doing a quick review, a relatively quick review, I'll just assume that this is a standard implementation and Andre hasn't inserted any backdoors here or anything. Okay, we'll move on. Seems quite standard till now. One thing, yeah, I'll just move on for now. See, I'm still glancing over everything to just if anything catches my eye, I'll stop, but everything till now has seemed standard. ERC20 interface, Oracle interface, and this is our main contract. Finally, after 500 lines of code. Okay, so we have about 200 lines of code in this smart contract. Let's just read what it does. So they have hard-coded an Oracle address. I'm actually look at Etherscan what page this is for. I think it's a generic Oracle, not for specific Oracle. This is the Uni v3 Oracle helper in some sense, I believe. We'll skip over this for now. Assume the Oracle is honest. Duration, precision, devap. Okay, this like immediately tells me that this contract is um, like inspired by the MasterChef contract from SushiSwap. This like style of maintaining debt of user reward and the reward separately is just that I think was done first in MasterChef contract. I might be wrong, but this tells me that this is that style of contract. So I'm just like connecting the dots here. Now I already have put in a list of common like pitfalls that people fall into when implementing contracts like that, and I know a few hacks that have happened on similar contracts in the past. So those vulnerabilities I will be verifying later. Let's just keep continuing on with the broad architecture first. We have the option struct. Here, one thing I'll just say, although it's not important from security point of view, but one thing you can do is pack these fields together. Boolean is just uint 8 in Solidity, and a field is uint 256. Uint also implies uint 256. So expiry, I suppose, is a timestamp. In uint 32, you can fit timestamp up to 2032, I think, or whatever. So you can like use uint 32 here as well. And if you use uint 32, the bool will get packed together, and you will now be using one storage slot rather than two, which reduces your gas costs. If you want to be safe, you can also use uint 64 or anything higher than 32, and uint 8 and 64 still get packed together because 64 plus 8 is less than 256, and every slot is 256 bits in Solidity. This is your balance amount, and this is, I suppose, the strike price. These, I think, although the amount is in uint 256 in ERC20s, but in reality, it will likely be it will fit into uint 112 or uint 128, let's say a more standard number, because that is the limit that you can use in Sushi V2 pools. You can't put in more amount than that. So I think it's fair to assume you won't be putting more amount than that here either. So, and strike price as well, it's just a price. It can say easily fit in uint 128. So I will recommend packing these two together as well. Uint 128 plus uint 128 plus uint 64 plus uint plus boolean is uint 8. Now you are using one slot for this, one slot for this, rather than total 4 slots. You have cut down your gas cost by 50%. You can actually go one step further now. So uint 128, that's fine for amount. For strike, you can be a bit like you can use less like bits for strike price, because I don't think like the price will need such a broad interpretation or whatever. If you use uint like 64 minus 8 will be 56. If you use uint 56, I think you should have sufficient bits to express whatever price you want, while still being able to pack all 4 of these in a single variable. So 128 plus 56 plus 64 plus 8 will give you 256, and this means that this whole struct is now just one storage variable. You have gone down from 4 storage reads and write on every read and write to just one storage read and write. Although like this doesn't affect security, but it is like a gas optimization that I'd usually add as an informational comment in my reviews. Okay, so we are storing an array of options, and next index is uint 8. And we have a mapping of address to balance of the user. Let me check one thing in the ERC20 if this balance of shouldn't be overloaded, but I'm just gonna confirm that it's not. Yeah, so this like ERC 721 uses holder tokens rather than balance, so we are good. I was just verifying that this is like not, this variable does not override the ERC721's variable. Although I was like fairly confident it does not, but whenever you come across something that you may not be like sure about, it's always best to refer back, just like I did. Then we have a constructor where we are setting a few parameters. Last time reward applicable. This is fine. Reward per token. This again does something similar to what MasterChef does. So if anyone has seen the Sushi Swap's MasterChef contract, they will recognize this style of coding. Earned is just returning the amount earned by the user. These I'll skip. So yeah, deposit functions. Okay, so we have two deposit functions. So this is function overloading. The parameters are different. If you call the deposit functions without parameters, it will just like issue this token. I suppose it does an issue or whatever position it is giving to the user, it will give it to this message sender. Well, in this case, the recipient is different from the message sender. Okay, so we have a couple more deposit functions. Amount, so if you want a custom amount rather than all of your balance, and if you want both of them as custom parameters. Okay. All of these finally call this internal function. This updates the state of the message sender and takes the tokens from the message sender to this address, increases the balance of the message sender of the two, which is the recipient, usually the message sender, and also increases the total supply. It emits a deposit event. We have a withdraw function that is supposed to do the reverse of deposit. Here we have similar 4 functions, and withdraw does indeed reduce the total supply, reduce the balance of the message sender, updates the message sender state, transfers the stake token that you originally logged to the recipient, and it's not doing the reward here. Maybe it transfers the reward in update. And yep, that's it. So the claim function, this one, let's see where it is being called. Okay, so this is just to claim the rewards of the message sender. This is interesting. So we are getting price of the asset. We are getting the expiry of the asset, of the option, which is block timestamp plus a hard-coded number. Then so for rewards, we are basically giving options to the user. So here, when the user claims the reward, we are just giving them an option. We have pushed the option here, amount, strike price, and stuff. And minting, we are minting message sender, next index. So this next index represents your option in this options array, and we have minted this. I suppose this is the ERC721 function, which and this like NFT is minted to the message sender, and we have emitted a created event. One thing I will point out here, so since the withdraw and deposit function supports a recipient address, one feature to add will be to also support a recipient address here in the get reward function, so that like you can mint to a specific address rather than yourself. No security concern here, but just makes sense to have that feature. So redeem is approved. So I suppose this means someone is exercising their option. Yep, no other option to exercise. So something happened. Is approved or I'm not sure what I'm clicking. Just so this checks that the token ID exists and the owner, the spender should be the owner, or the spender must be approved by the owner. These are your standard ERC20, ERC721 function, or if it's approved for everyone. This should never be the case in this. But yeah, so this just verifies permission. That is good. This reads the option from storage. This verifies that the expiry is greater than the timestamp. So this means that the option has not expired yet. And we are also checking that the option has not been exercised yet. So once we have verified that, we do a transfer from message sender to treasury. So when you exercise an option, as I said, you need to buy the token. So you are buying chat token. Let's say the buy with currency is USDC. So you will be transferring the like strike price of that option, which is like the price you that was fixed earlier that you will be buying the token for, to the treasury, and this does that. Safe transfer does basically like it transfers the reward to the user. So this is now transferring the CHAD token to the message sender, and this is the amount that it is transferring. So it makes sense. You pay for the token, you get back the token. After that, we are setting the exercised variable to true and options. Okay, so we are this is unnecessary. So the reason I say that is you see here, this opt variable is already a storage pointer. So this means that anytime you read this, it will be read from the storage. Anytime you modify this, it will be written directly to the storage. You don't need this line at all. I'm not 100% sure if Solidity does optimize this away or not, but in the most naive case, this will cause the Solidity compiler to go to the storage pointer, read everything from that storage, and then put the same thing back into the same storage literally. So you're reading the same content, putting the same content back here, which is just waste of gas. This line doesn't do anything. If this was declared memory rather than storage, then you will need this line, because memory means that rather than this being a pointer to the underlying storage, you are reading the storage right now and saving all of the data in the memory. So whenever you like read this variable later, you will be reading directly from the memory rather than from storage. You will be saving gas. And whenever you write to this variable, if this was memory, you will be writing to your variable in the memory. You will not be modifying the storage in that case. So in that case, you would have needed this line to actually save the changes in storage. But in this case, this line is not needed. Get rewards. This is a function just to claim the rewards. This, I think, is the most important modifier in this contract. We'll come to this in a bit. Exit allows you to withdraw. Does the interlink withdraw call update? Yes, it does. So it will this just combines your get reward and withdraw function. You like this will be the case when you want to exit with the reward. I think like one comment I'll add here, since that function is missing, there should also be an emergency exit function that will allow people to withdraw their deposit without getting any reward. So like if someone like for any reason, if there was bug in well, it's not really relevant here because we are only issuing options when minting options. So this should always succeed. But in your traditional master shift contracts, if you were just giving out rewards directly, you would want an emergency exit function, which people can call to exit their positions if the contract has run out of funds to like give away. In our case, the contract will never run out of funds because it's not giving away any funds as rewards. It is giving options which it can mint from thin air. Claiming or redeeming these options will fail if the contract is like out of resources, but at this stage your original collateral is already safe. Okay, so what does notify do? This is weird. This function is transferring like reward token from message sender to this address for this amount. Okay, so yeah, I think I know now. So this the caller will first of all need to approve this smart contract to transfer the functions, transfer the tokens, and I suppose this function is to like fill the contract with funds that it can like give away when people redeem their options. So if you were the treasury of the protocol, you will approve this contract, and then in future, if you want to top it off with more tokens, you'll just call this notify function with the amount, and the contract will take that much amount from your balance. I'll look at the rest of the code to ensure my assumptions are correct. Yeah, it's just updating some reward rate stuff. Yeah, so whenever you transfer the tokens, it does change your reward rate because now, although the time has stayed constant, the funds available to December's have changed. So now you have more funds available to December, so you have a higher reward rate. But this seems problematic. Let me drink some water. So first of all, the problem I see here is that there is no check who can call this function. So anyone can call the notify function and trigger this clause, which will change a bunch of variables. Now we need to verify that these variables, like changing these variables, can cause a harm or not. From this, I'm seeing it is direct. So this can only happen when the period finish has already happened. So the original like contract has like original options offering has been completed. Only then you can call this function. Only then you can enter this else if clause, and in this case you will set the reward rate directly to the amount divided by duration. Last update time will be increased and or like set to the current time, and period finish will be updated. So I don't think this causes any loss of funds, at least this if statement, but I can see a potential DDoS attack vector here. If the period actually did finish and now the DAO is creating a new LM mining program and is starting a new options offering, they probably will call this function so that this can be triggered. But someone can front run their transaction and like call this function themselves and approve this contract to transfer like one way of tokens. So they can put in the amount as one. This will succeed. This case is now true. This will succeed. The reward rate will be set to 1 divided by something, which will be 0 because Solidity does not deal with float points. So the reward rate now will be 0. The contract will not be giving away rewards. The last update time will be set to this, and the period finish time will be set to period block.timestamp plus duration. So this means that you will no longer be able to enter this if clause. We'll see if the else clause can like handle that, or does it make it like problematic or not. But by front running the call, you are making the DAO to not be able to enter into this if clause. In this else clause, we see they are calculating remaining, which is the period finish minus block timestamp. This can be 0, this can be 1, this can be anything. Leftover tokens are the tokens that are left from giving away the reward already. I see a very small. So two things I've already noticed. One is that the DDoS vector is not very problematic, because the else statement also does basically what the if statement does with just extra checks. So even if someone front ran you, there isn't much of a problem. But there is there's no problem here either. The leftover is calculated if you call the function in the same contract, then the remaining leftover will actually be the remaining will be 0. Oh no, remaining will be period minus blocks timestamp, so the remaining will be duration. And then the leftover will be duration multiplied by reward rate, which we see from here. Duration multiplied by reward rate will give you the amount. So now here you have the leftover is equal to the amount that the person deposited. And if we call this function sometime in the future when the mining has already started but not ended, then also we'll get the proper leftover amount here. Reward rate will be updated plus leftover by duration. Last update time is this, period finish is this is good. So we are just updating the reward rate of this contract in this function. Okay, now the update modifier, this was being called everywhere. This is the most important modifier. Reward per token. I guess this just gets your reward rate. We'll look at this now. If total supply is 0, returns the stored one. If it's that. Otherwise, the saved reward is fine, but to that we'll add last time reward rate applicable. Yeah, so this just gives you the timestamp where if the period has finished, then the reward should finish at the finish date. If the period is still ongoing, then the reward should continue on, and the current time should be used to get the last eligible date. Basically, we do that, we subtract the last update time. So if we are doing this, then that means since we changed the reward rate on this time, that change is already included or should be included in the reward per token stored variable. So we should be doing all new calculations based on the new reward rate and the new last update time. We are just doing multiplication with precision, dividing by total supply. All of this is good. We are just returning the reward per token right now. This is like the value of 1 token deposited. That's good. This has been updated. This is the storage variable. Last update time, this has also been updated. That is also good. If the account is not address 0, then we should update the reward details of the user. So user reward per token paid. Okay, so first we are setting the rewards already accumulated by the user using the earn function. This, I guess my right click is not working properly. Anyway, so the earn function returns your balance multiplied by reward per token, subtracting user debt precision. Yeah. So this just returns the total reward that the user has earned till now. Okay. Yeah. So this portion calculates the new reward that the user should be given. And then we add the previous reward to this. So this gives your cumulative reward for the user. So this is one place where this contract deviates from the MasterChef. In MasterChef, you don't store the reward separately. You just use the debt and calculate rewards on the fly. But here you are changing rewards because you can change the reward rate in the future. Okay, so we calculate the user rewards and we store the current reward rate per token, which is later used in this earn function for the user. That's all good. And I just verified that even you call notify, that is when you are changing this reward rate, you are also making sure that you update the reward per token stored before these changes are executed, so that you have covered the current reward calculations based on the current reward rate. I think everything's cool till now. So at this moment, from a brief overview, I can say, like, assuming that these safe transfer functions are actually safe, then then I don't see any major issues with this smart contract, apart from some gas optimizations that I've already mentioned. But otherwise, this does seem like like it is doing what it is supposed to do. I'll also take a look at. Okay, so this token is not ERC20, right? This balance of, I just want to make sure that this balance of can't be modified by anything really. And this is just a view function. This can't modify it. Deposit obviously adds to the balance. Withdraw is reading right now. This subtracts from the balance. And exit takes out all the balance. Okay, I see one potential issue. Okay, so I'm just gathering my thoughts here. This might be a critical issue, but so the like again, this method is like one of like common pitfalls of developing MasterChef like contracts. So I've seen this kinds of errors before. And that is how, like, this is just like one line of thinking I'm approaching right now. At this moment, I don't have confirmation that this is an issue, but from the stuff I'm seeing here, this is a potential attack vector that can be an issue in this type of smart contract. So let's verify that live. I'll first briefly describe what I'm thinking. So as you can see, this smart contract mainly like heavily relies on this update modifier. This debt of the user, this reward per token stored, this signifies that the portion of rewards that should not be paid out to the user. So these rewards have either been already paid out or like the user entered after they were eligible for these rewards. So this is a very important variable in these types of smart contracts. And this modifier is called on every deposit, withdraw, notify, everything. That's all good. But the potential problem I'm seeing is that we have functions like this deposit, where the recipient of this like token of this like balance can actually be someone other than the message sender. So you will see here the parameters are being updated for the message sender, but we are actually giving the tokens to the to address recipient, which can be someone else, which means here I'm not seeing any place where we have updated the parameters for this recipient. This means that this recipient still has their like variable, this important variable, initialized as 0, rather than this being the current value of the reward per token. So now that we have established that this variable is still 0 in the like receiving address, now the recipient has some balance. You can see the balance of 2 has increased, but their like debt has not been increased. Now what the user can do is, from this to address, call the withdraw function. So this withdraw goes here, this withdraw goes here, this withdraw goes here, and this updates the message sender. That's good. We are calling from the recipient this time. So we'll again follow this update modifier. Yeah, so now we are entering the update modifier, which the address of the user of the recipient address, which currently has the reward per token paid set as 0. So we see that this calculates the latest reward per token, which is a global variable. That's all good. We want that. It calculates the last time reward reward applicable. So whenever was the last update time. This is another global variable. That's all good. We are happy. Then it enters this if case and it calculates the rewards that this user should get. This is where I think the problem lies. You will see we know the balance of the recipient is a high number, whatever we minted, that's good. This variable is a global variable, which is a high number, that's good. This should have represented this user reward per token paid, should have represented the starting reward per token for the user. So this should have represented the value of a token when the user entered. So this value should not be paid out to the recipient. That is why we are reducing this value from reward per token. This basically represents the amount that the user has like either already claimed or they are not eligible at all. For a normal user, if they had called deposit function with their message sender and message sender as a recipient, this would have been a very high number, almost same as the reward per token, exactly same within the same block, but later this one would have slowly increased while this would have remained constant. So the resultant of this would have been a small number, and the final result would have been also a small number. Balance multiplied by a small number gives you a small number. Precision you can ignore. Also this addition of current rewards of the user, this also you can ignore. The current rewards are 0 for our user. But in our use case, when we are using the recipient accounts, this variable is 0. And I think this is a critical vulnerability. Now you are paying the user from the first date that the program started, rather than rather than paying the user from the date they entered. So if someone enters the liquidity mining on day 30, let's say after 1 month, and they used this trick, they will still get rewards like whenever they claim the reward. Let's say they claim the reward on the same block itself, like they do a deposit transaction and they immediately withdraw their balance. Ideally, these two variables should have been same, so they get 0 rewards, but due to the trick we discovered, this variable is 0, so the reward they are getting is the full reward from day 0 up till now, and that is how they can get more rewards than they deserve. And I think this seems like a critical vulnerability to me. Um, I might be missing something. Obviously, like if I was doing a full audit, I would create a POC at this point and talk to the dev, Andre in this case, to verify my findings, and to see like if I've missed anything or whatever. But since this is just a quick review, I think I will just end it here, saying that I think this seems like a potential critical vulnerability where you call a deposit with a recipient which is a new address which hasn't interacted with this like contract before, and then you immediately withdraw the balance from that recipient, and you get higher rewards than you were supposed to. Okay, I'm gonna take a small break now. Break there. I'll check the chat if there is anything interesting there. So on the selector comment, I suppose you meant, yeah, these ones. So yes, these are selectors in Solidity. Like these can be selectors, but let me verify what they are being used for here. Oh yeah, these are being used to register the interface. My right click is done for. So we'll fall back here. So these are not, doesn't seem like these are Solidity selectors, although Solidity selectors are also bytes 4. I'm not 100% like, I don't remember this ERC from top of my head. I'm not sure if this byte 4 is supposed to represent the selector of the function, or a code that is like decided elsewhere or whatever. But the syntax is same for Solidity's function selectors as well. A bytes 4 variable where which is basically a kcac hash of the signature of the contract, which is this. And we take the first 8 digits or first 4 bytes of that hash. That becomes the function selector in Solidity. So for Hex, guys, I have Hex in extras, but I won't be able to get to that, unfortunately. I'm already, I think, going slower than I was anticipating. I want to cover these smaller tokens right now. Hex, I briefly looked at. It is 3,000 lines of code. If I start reviewing that, it will take longer than I intend to run this stream for. One bug, please. I think I just found a critical bug in Andre's smart contract. That should be good enough. How is UN 256 physically stored? That is a weird question, Sankrant. So physically, it really depends on the software you are running. Ethereum does not mandate how it should be stored physically. So it really depends on the client that you are running. From the EVM perspective, which is the Ethereum's virtual machine, they have like 256-bit storage slots only. So everything is stored in 256 bits, and everything is like encoded as bytes and stored in that storage slot. You can like call it raw bytes, bits, or whatever, but everything is 256 bits in EVM. This stream, I will make it available in my videos once it is over. So the plugin for these arrows is, I think, Solidity Visualizer from Tintin. Memory is more expensive than storage, so that is not true. Changing a variable in memory costs, I think, 100 gas, while storage write is 20,000 gas for a new variable. Storage read is 2,100 gas, if I remember correctly, per variable, while in memory it is maybe 50 gas or something like that. As for gas optimizations, I'll talk about the whatever points I see in the contracts. Other than that, I have a couple of blog posts that you can check out on moded.blog, where I gave some solidity gas optimization tips a couple of years ago, but most of them are still valid. How is divide by zero handled? That causes a panic in the EVM. It causes a revert. All of the state is reverted. Well, I see it. Okay. Yeah, this is the same, like someone mentioned that the reward distribution bug is the same as the one that was in Popsicle. And you are right, this is the same bug, or not exactly the same, but the similar class of bug that was present in Popsicle Finance. I did a Twitter thread on that. If you want to read about it, I went into more details about it. But yeah, this is the same class of bug. Okay. 2 times a week. I will try to do more streams in future like this, but I'll be honest, it will be hard for me to find time to do 2 every week. I'm like, this thing I'm just doing like out of passion or something. So I don't want to commit to it really. I will do it whenever I get time, but I don't want to take on any commitments at the moment. I'm happy that you guys are liking it. Can we replace the 4 withdraw and deposit into one with if else case? Yes, you can. The reason you split it into different functions is that way it is like 50 gas cheaper. You're saving one like if else loop or whatever. So yeah, that is like the reason for splitting in 4 function is some gas optimizations only. The tech analysis for that, actually, let me just open up my Twitter and I'll post the link here. Okay, I think that will I'll post my Twitter link in the chat. You can scroll down and find that analysis. I don't want to like waste everyone's time on the stream looking at my Twitter timeline, but posted my Twitter channel and you Twitter handle. You can scroll down and find that thread there. Okay, I think I've caught up with the chat now. Let's move on to the next contract. Paywall.sol. So now I'll try to go on a bit faster. It's 10:30 p.m. here, and I want to end the stream before midnight. Yeah, I will be going a bit faster. So some context, a lightweight payment contract for access to non-tokenized digital assets. You can create paywalls for articles, courses, and other digital content where users pay with their Ethereum, Polygon wallets in this case. So yeah, this seems your like normal paywall where to access some content, you need to pay up. So most common example I think will be news websites like New York Times. They offer you like some free articles per month, and after you have consumed them, you have to pay a membership fee to access more content. The Block has a paywall like this, Medium has a paywall like this, and a lot of folks have a paywall like this. It is definitely an interesting idea to create a decentralized paywall where people can pay via like their Ethereum wallets or whatever directly. So let's delve into this contract. This variable, I suppose this contract keeps a fee of the like paywall. So if the content creator sets the price as 1 ether, this contract will keep like 0.1 ether or something as fee and give the remaining 0.9 to the content creator. Again, this is just an assumption I've created from this line, from this comment and line. We'll verify if my assumption is correct later on. Since I don't have a lot of documentation to go off from, I'm just creating a mental model in my mind itself to like just coming back to my audit methodology that I described before. I try to create a model of the contract before I actually look at the contract. Contract fee, a fee accrued by the contract has access. So I guess this is this is set after someone has paid up, so it gives them the access. So we have multiple owners. That's good. Okay, so this ID basically represents your content creator ID, and this address is the content creator address. This is the pending money that the asset owner has not withdrawn. This is also a mapping. So on content creator ID to the amount they have not withdrawn yet. And this is the fee amount. And this is the paywall amount that the user has to pay. Again, this is from per content creator ID to the amount that the user must pay up. That's all good. Just an event. We'll ignore that. The only asset modifier is fine. So another quick tip about Solidity. The whole reason string that you enter here is stored in the bytecode of the smart contract. So if you are like an Ethereum EVM also has a limit of 24 kilobytes on the size of bytecode of one smart contract. So once this contract compiles down, it can only be a maximum of 24 kilobytes or you won't be able to deploy it. Since this whole string is part of the bytecode, this increases the size of your contract. So if you are ever in a situation where your contract is exceeding the size limit of Ethereum, you can shorten this string to fit into one slot, which is byte 32 or 256 bits. Just count 256 bits from here, or like I think every character will take 8 bits. You can count it from that. So anyway, since EVM or Solidity also just works on 256 bits at a time, if you enter only O here, you will still be using 256 bits in your storage, in your space. If you enter 256 bits, you will still be using 256 bits. If you enter 257 bits, you will be using 512 bits of storage. So first try to make sure that the error fits inside 256 bits. That's cool. And if you are even if you want to save even more gas, just get rid of this string completely, and now you have saved even that 256 bit. Okay, so create, anyone can call create. I guess this creates a paywall. Counter is auto incremented, the amount of counter. So this is your content creator ID. It is set to the fee that the user sets. The owner of the counter is set to the owner, and that's it. So this function looks good. Grant access. So I guess this is the function that the user calls to get to pay the paywall fees. Okay. You provide the content creator ID, you provide the address of the contract that should gain access. So this means you can pay for someone else as well. If the contract had used message sender rather than this field, then you would have been paying for yourself only. So this just checks that the counter exists. The message value is ensured to be exactly the fee amount. Can the user change the fee amount? Okay, so that's fine. This ensures that the address does not have a does not have permission already. So one like code quality improvement here, rather than equal to false, maybe this is personal opinion, I just do not here. This means the same thing, but like to my brain this just looks cleaner. Under the hood, I think Solidity will compile both of these to the same. There can be one potential like optimization here where they don't push false to the stack, but they will be pushing false to the stack. Sorry, I'm just thinking out loud. So I think the underlying code will be the same, but that's just like personal opinion. So here we calculate the contract fee amount. So we multiply the message value with the contract fee and we divide it by the fee base. This is the maximum fee, or like 100% fee will be this value. And this is the actual value. We do this because we can't enter numbers in decimals in Solidity. So if we wanted to take 0.1% fee, then you can't enter 0.1 here. What you'll have to enter is 1 here and 10 here. That gives you 1 by 10, which is actually 10%, not 0.1%, but you get the point. You can't enter decimal points or percentage here. Okay, so then we have the amount that is given to the owner. We are doing a sub from the message value. We reduce our fee, and this is what the owner or content creator gets. We increase the content creator's pending amount by this, and contract fees accrued by this contract fee accrued, and we grant access to the address to the user. Everything seems fine. Just one thing, one issue, potential issue I've seen here is that if this contract fee is modifiable by the contract owner, then they might like start their contract with 0% fee and at a later date just modify it to 100% when the users are like buying in the content. The user will not realize this because they will still get access, and the content creator might take a few days or weeks to realize that the fee has been suddenly increased to 100%. So this is another case. I'll suggest if this variable is changeable, it should be changeable via only a time-logged multisig. So here we can see the owner can change this variable, this fee. So to this project, my advice will be to make sure that, okay, so I suppose this inherits ownable, yeah. My advice will be to make the owner a multisig, and that to a time-logged multisig, so that any change that you do is like it goes through a waiting process or something like that, to avoid these like sort of rug pull situations. Not exactly rug pull, but something similar situations. Okay, let's continue back on here. We have identified one issue that here. That's fine. Withdraw allows the asset owner to withdraw funds. We require that the funds should be withdrawable. We get the asset owner address. We get the amount to withdraw. We set the pending withdrawal to 0 and we transfer the amount. So this is good. They are doing the changes to storage first before doing the transfer. So even if this call was to re-enter, now it will see that the pending withdrawal is already 0 and cause a revert. So that's good. No issues here. Okay, change the asset fee. This we have already talked about. Oh no, this one is different. So this is the fee that the user pays. This one I think is fine. It can be 100% dependent on the content creator, because it's a mutual agreement between the content creator and the user how much fee they are willing to pay. There is no third party involved, and therefore we do not need a multisig or a time log basically. Obviously for the asset owner, it's best to use a multisig for these functions, but we don't, a third party does not need this. The situation where you need a time lock is when your changes affect a third party. In this case, they do not. They only affect you and the buyer of your content. So we don't need time locks here. Change asset owner, same thing. Don't need any. We don't need any anything else here. Contract fee we have already talked about, and contract withdraw only owner can call. This is fine. Fee accrued must be greater than 0. And again, they have done the right thing here by setting the variable to 0. And they transfer the ether fee. So this is an interesting hack. By the way, if you do not have this receive function at all, Solidity will automatically cause a revert. You don't need this function. So the author's intention here is that people don't directly send any ether to this contract. They always send ether by calling this grant access function. I think they are on the right track, but maybe a bit too verbose. So while we're talking about this, some more smaller things you can do. If you want to use require, you can just put false here rather than 0 equal to 1. And if you want to cause a revert, you actually don't need require. You can just use revert directly. This is another function in Solidity which just causes a revert. You don't need to pass anything. Just you don't need to check any condition. Pass your condition here, and it will cause a revert and forward this condition. So yep, that is it. I think paywall review is done. Nothing critical found. Just one anti-rug pull suggestion to use a time lock contract for the owner. Okay, I'm gonna look at the comments now. So on Diamond storage, it does solve your issue of 24 kilobytes, but it does it adds extra complexity and gas cost to your call. I don't have anything against using it, but it is not a one solution fits all situation. In some scenarios, Diamond proxy is useful, but not always. Best practices for fallback and receive. So not really. The best practice honestly is to not have a fallback or receive function, which means that if someone sends ether to your contract mistakenly, it will cause a revert. But other than that, if you need a receive function or if you need a fallback function, there aren't really any best strategies or whatever for it. It really depends on the use case that you want. Okay, let's move on to the next one. So we have a time lock function. This is what I've been talking about for a while now. Access control, I'm gonna assume this is just a standard contract from maybe OpenZeppelin or something. I'm gonna ignore that for this review. We have revert message extractor. This is another library we are gonna ignore. Is contract library. So this makes sure that the contract has been deployed in some prior transaction. So while I'm here, I'll just add one comment about it. Yeah, this line basically. So this is not a foolproof method. You can bypass this check by making calls in the constructor of your contract deployment. So if you are deploying a contract and in the constructor, you call another contract, and then that contract uses this library to check if you are a contract or if you are an end user, it will get an incorrect result because your contracts, the one with the constructor from where you are calling, where you are deploying, on the blockchain, this has not been deployed yet. Your code is still 0. although you are calling from a contract, but it will be deployed only after the transaction ends. It is currently being processed for deployment. So in those scenarios, these checks can be bypassed. So like people should be like aware when using this check in their contract. That is like an attacker can still use a contract to interact uh, with your this thing, time lock contract or whatever. Let's move on. So we have grace period, minimum delay. So this is your execution delay, I guess. The minimum number of days you must wait before executing a proposal, maximum number of days you can wait before executing. Grace period, I guess it is like it must be 14 days extra on top of maximum delay, but we'll see later. Delay is stored in a UBIburner.32. Another quick tidbit about EVM. If you are not packing a UBIburner together with anything, you can see this is a UBIburner.32, so it can potentially be packed with other storage variables, but it is not being packed. So it is actually a bit gas efficient to use UBIburner.256 rather than UBIburner.32, because EVM always works in 256 bits. So even if you provide just 32 bits to it, it will have to do that conversion, and that conversion will take just a little bit of gas, maybe like 10-15 units or something. It takes a very small unit like amount of gas, but it does consume extra gas. So it is best to just use UBIburner.256 when you are not packing your variables. Similarly, if you are using variable in a function in memory, then again, same story applies. You should use UBIburner.256 here. Like if you're defining a variable here, UBIburner.256 something, you should be using UBIburner.256 rather than UBIburner.8 or whatever, even if you only need UBIburner.8, because in memory as well, Solidity, at least it used to, I'm not sure if they changed it recently or not, but Solidity always assigned 256 bits. So if you used a variable smaller than 256 bits, you are just making the EVM do more work in those like conversions and all. So it's better to use 256 bits directly. Not a security concern, just a minor gas optimization thing. Okay, we have a constructor that gives away a bunch of roles. So these are the function selectors, and the governor, I guess, gets most of the permissions. And changing the delays can be done only by this contract, not the governor. This means that the governor can't just bypass the delay by changing the delay itself. The governor will have to create a proposal in this contract itself, wait for 2 days to execute for it to execute, and that proposal will be able to change the delay in this contract. So this address also gets the root access. So this a proposal can call anything, and the message sender, I guess by default access control gives root access to message sender. We are revoking that access here. Let me grab some water. Okay, set delay auth is from the access role. I'm going to assume that this auth modifier works correctly and has been implemented correctly. In an audit, again, I would have verified this, but for now, let's just assume that is correct, which means that only this address should be able to call the set delay function. We just do some checks and change the delay, so no problems here. Then we have a propose function that takes an array of addresses to call and data to call these addresses with. Again, we have auth permission, so only the governor should be able to propose, and it returns a tx hash. We call an internal propose function. Then we have a propose repeated. Okay, so this adds a salt so that the TX hash that you get from the same data is now different. This calls the same underlying propose functions. No problems here. So one gas optimization. You don't need the function modifier in all three of these, auth. You can have this only in this internal function and remove it from here. Or actually, you can remove it from here and only have this here. Either is fine. Like either you remove it from these and just have it here. Or you remove it from here and just have it here. I say that because this is an internal or private function that this cannot be directly called anyway. So there is no reason for us to check permission at two different places. Here we first check that the user should have proposed permission, and then we check that the user should have underscore proposed permission, which I think is a bit like unnecessary. You can only check if the user has underscore proposed permission, or you can check that the user has proposed permission. So just one gas optimization there. So yeah, this check verifies that the target's array list is array has the same length as the data length, data array length. One way to avoid doing this check, and I think a neater approach overall, is to create a struct which has a target and a data. So we define a struct as something like this, where we say we have an address and we have bytes data. And then the input, rather than being these two different areas, the input becomes param all data. Now you can just iterate over the length of this param and get the data and target for every I. The advantage, you don't need to do this check. Solidity encoding decoding naturally mandates this check, which means that this core is likely going to be a bit cheaper, but only by a bit. Then another advantage is, I think this just looks cleaner, which is like a personal opinion. But yeah, I prefer this approach over multiple arrays. Moving on, this calculates the kchak or however you pronounce it, hash by encoding the targets, data, and salt. That's all good. Now this can be modified by the proposer. I understand that, like, since this is an array, you just change the order of that array and you will get a different hash, although the actual elements will be the same. Which means, like, since we are already trusting the governor, I think this is not a problem. This is fine. But if it was an open system, maybe this could have been an issue. Then we ensure that the TX hash is already an unknown proposal, that it has not been proposed already. We set its state to proposed. That's all good. And we emit some events. Then the approval is called after the propose has been called. So once the propose has been called, we call approve to approve this proposal. So we ensure that the state is equal to proposed. This approve can only be called by the governor. Again, nobody else can call this. And state is set to approved. The ETA when this should be executed is set to timestamp plus delay. This is the minimum time after which the thing can be executed. So yeah, above, like, I can correct my understanding here. These are not the delay that are currently present in the smart contract. These are the minimum and maximum values that the governor or this contract can set as delays. The delay is a fixed value that is defined here, and that means this grace period is delay plus grace period when you can execute the contract. when you can execute the proposal. Okay, so the ETA is set, state is approved, ETA is set here. You can save a few units of gas by just saving ETA here directly. Even then this should get packed, so that's fine. Proposal's TX hash is set to your whole proposal. Okay, so an alternative approach here that wait actually okay, so that is fine. You're using memory here, and that is why you have to write it separately. I don't think I've seen the proposal struct. Oh, it has a state and it has an ETA. So no additional packing can be done here. Both are packed together. This is all good. Execute again takes the same data and calls the execute function. This again can only be called by the governor. And the underlying function, same optimization can be done here. We only need auth on either this underscore execute or both of these two functions. Okay, we calculate the TX hash live. We fetch the proposal details. We ensure that the proposal is approved. And we ensure that the block timestamp is more than the ETA and less than the grace period plus ETA. That's all good. And then we delete the proposal. So that this can't be like once you delete the proposal, you can't re-enter with the same proposal, and we just empty up some storage space. We create an array of all the results. We iterate over the targets. One thing I'm just thinking or something. So here, these guys are not using is contract to stop contracts from like doing some stupid shit, but they are using is contract to actually as an additional check that we are creating proposals and calling contracts only. So even like a contract bypassing this check here doesn't make sense, and this is a perfectly valid use case of this check. So for all the targets, we do a low level call. We call the we copy the data. We call the target. If it's not a success, we cause a revert. If it is a success, we put the result in the results array, and at the end we emit the executed event. So no problems here. I'm just thinking about some attack vectors here. That is like if you can somehow re-enter an important function within the execution of the proposal. We would have been able to re-enter if this delete wasn't here, but since this deletes the state, even if you re-enter and like propose something, it will add it as a new proposal which is unapproved, and like the ETA is this thing, like when you approve it, the ETA is set. So from a quick review, I think everything is working fine. Just one quirk that I would point out is I think since only the governor can both approve and propose, it would be nice to have a single function called propose and approve or something like that, where within a single function you can both propose a proposal and approve a proposal rather than having to make two different calls. Other than that, this contract looks good. It is high quality code, so yep, nothing else, nothing obvious here anyway. Looking at the comments now. Okay, so this time I have a bunch more comments. Most of them are about a certain project that I'm just going to ignore. I honestly have not looked into that project to make any like comments or whatever. I'll just start this. It's nice to be skeptical of new projects. You should do your own research before putting your money in. Do not trust what influencers say. Influencers are rarely honest in my experience. So it is nice to see that people are skeptical, but I'll leave that at it is. That I leave that there because I don't have a clue about what Higgs is. I've seen them everywhere, but I just don't want to look into it. Honestly, I haven't got the time to do that. Moving on to the next contract, we have this UBI burner. So this was the comment I got here. This exchange is okay, so it swaps one token and freezes. Does it freeze the ETH? I guess so. I guess what he's trying to say is they are trying to say here is in this function the user will provide a token, the contract will swap that token for ETH, and then the contract will keep that ETH. Now let's see if my assumption is correct. This is the interface for Uniswap v2 router. This is the router address, WETH address, UBI token address, and this is the path. Now if it was a full audit, I would have verified that these addresses are correct, but again for now I will skip that. So burn UBI, we have this function here, get amount of, this is a view function, this is a view function, and we have a receive which just receives ether. So yeah, the user was right. This is the main function we want to look at, and yeah, this is a like a small contract, so shouldn't take long to review. They also have friendly comments. I'll read that by UBI. Okay, so they are buying UBI token. They are not selling UBI token. Interesting. Interesting. So they are not selling the token, they are buying the token. So people are supposed to somehow this contract is supposed to have ether in it, and people are anyone is allowed to use that ether to buy this UBI token, and that UBI token will forever be logged in this contract. I'm not sure how this contract gets ether. It can't get ether in this call because it's not a payable function, so it must be getting ether from an external system, and we're just going to ignore that fact and assume that there is an external system that funds this contract. So with that assumption in mind that this contract is already funded, we are not taking any funds from the user. Let's move on to the next assumption, next thing. So this says that minimum, okay, this is not good, but so let's first look at this function, what it does. here's the interface. The first parameter is amount out minimum. This is the minimum output token that you are willing to get. So if the pool is let's say at a state where 1 ether costs 3000 USD, and if you give 1 ether to the pool, you would want to get 3000 USD back. So you will put amount out minimum to maybe like 2999 or something like that. Just give some leeway to the contract in case the price changes before now and transaction gets mined, but you make sure that you at least get most of what you were expecting. Then this path is like whatever you are swapping. With to UBI path implies you are putting in with and swap and getting UBI back. 2 is the address that gets the output token. This should be address this in our case, and deadline is the last date you can execute this swap. It should be anything equal or more than the current block address. So this user is taking the deadline as a user input, which is fine, I guess, but they can also just hard code it to something high value, like they can use block timestamp +1 or just max UN 256, because since the user is not controlling the price, the deadline is not useful for the user. The amount, that's fine. The amount of ETH that should be put in. Okay, so this just calls this swap function, and here I'll explain what the issue is now. If you set the amount out min to a very low value, then you open yourself up to the sandwich attacks, basically, where someone unbalances the pool. So if you are in, let's say, ETH USD pool, every ETH, and you want to sell ETH for USD. ETH right now is worth $3,000, so you get $3,000 for selling 1 ETH. But if someone unbalances the pool by selling a bunch of ETH in the router, they will sell a lot of ETH. They will get that ETH via a flash loan maybe, or they have some big pockets. They will unbalance the pool, and now a pool will be in a state where 1 ETH is worth, let's say, only $1. It has already sold all its ETH. They will now include your transaction in the block. They will execute your transaction, which is this burn UBI. Now, instead of getting $3,000 worth by selling your 1 ETH, you're getting only 1 token back. So this, like, you would have expected to get 3,000, but you got only 1 token back. You have basically lost money here. You can't do anything about it. And in the second step, they will buy back the ETH for the cheap price. Now, since you have also sold ETH, the price of ETH has now actually gone down further. If they left it at $1, you have made the ETH price to go to maybe $0.99. So now when the attacker starts buying ETH, they will start buying at a lower price, and they will be able to make a profit out of your misery. Since they are buying ETH for cheaper than they sold it for, at the end they make a profit, and that profit basically comes from the loss that you have made by selling your tokens for cheap. The caveats here is that unbalancing a uni pool like this or sushi pool like this requires you to have a lot of liquidity, a lot of like funds. You can take a flash loan for those funds, and in fact right now KeeperDAO is offering free loans. You can borrow like 10,000 Ethereum. I think they have $10,000 million. Sorry, I missed the numbers. I think they have $10 million worth of Ethereum in their contract right now. They are giving as flash loan for free. Obviously, you need to return that ETH within the same transaction, but you can use that ETH to do these arbitrage transactions. That doesn't cost you anything. But one thing that will cost you is the fee in the Uniswap pool itself. In V2, the fee is, I think, 0.3%. So when you like take the price down, you pay 0.3% in fee. And when you bring the price up, you again pay 0.3% fee. So you are in total paying, let's say, about 0.6% in fee. So the profit you make should be more than 0.6%. So the amount that this function is swapping should be more than that fee for the attack to be like feasible for you to execute, or else you will also lose money. This user will also lose money. Only the Uniswap LP providers will gain money in terms of fees. If those caveats are fulfilled, this is ripe to being exploited in in sandwich attacks. Since this function can be called by anyone, people don't even need to do it in different transactions. They can create a single transaction which takes a flash loan, unbalances the pool, calls this burn UBI, and finally rebalances the pool. And then they also pay back the loan and keep the profit with them. So yeah, I think this needs a fix. So how can you fix this? That's an interesting question. If you want anyone to use your ETH to burn UBI, one way to fix it will be to use an external oracle like Chainlink to make sure that the price you are getting for UBI is valid. Or you can use the UniV2's. That is a bit more complex, but you can use UniV2's TWAP as well, and make sure that the price has not changed significantly in the last few, like in the last block or something. That will also fix this issue. Another option will be to make this function like permissioned and take this as a user input. So you as a user provide the min value so that you cannot get like sandwiched easily. You can't make this a user input without making this a permission function, because then the attacker will just enter one from their side. So yeah, this is although the contract is simple, this has one of the like DeFi hackable function or something like that. This is like one of the common DeFi pitfalls. A lot of projects have fallen like ill to these kinds of flash loan, oracle manipulation, and swap attacks in the past, especially on the Binance chain. That being said, if you expect to only be swapping like $10 worth of tokens on every transaction, then this is totally fine. Nobody will spend the gas or the funds required to do a sandwich attack for a maximum $10 of profit. So if a lot of things depends on your risk appetite and how you use this contract, but it is recommended to fix this. I'll now look at the comments again. I see still people are talking about a Ponzi. I'm gonna ignore those comments. Is KeeperDAO more gas efficient than DYDX? I have honestly not compared their gas efficiency, but one thing I will say this is KeeperDAO is easier to use, especially when it comes to documentation or something. I briefly looked at DYDX like last week, in fact, when I was rescuing, like I was in a war room for Misu, and DYDX documentation was a bit more like involved or like complex than Keeper. And since I wanted to get things done, I just went with Keeper. By the way, this is a good point. DYDX also offers free loans. I think you have to pay back one extra way in that case, but technically it is free. In KeeperDAO, you don't need to pay back any extra way. You can pay back exactly the same amount, at least right now. KeeperDAO, I think, has a function to increase the fees in the future, but right now the fees are 0. Okay, let's move on to the last contract. Last but not least, this is yield token compounding. So I actually know about this like project already. So if anyone knows about Element Finance, this is built on top of that. Element Finance has some yield tokens and some principal tokens, YT, PT, that you get by depositing your assets. So if you deposit your asset, you get a portion of PT and a portion of YT. So what this project does is it deposits your assets into Element. It gets some YT and some PT, and then it sells those PT for the underlying token. Then it again deposits those underlying tokens into Element, and now it again gets some PT and some YT. It keeps the YT away, it keeps the YT safe, and it reinvests, like sells the PT for underlying token, and keeps repeating the process. So it is like compounding your YT holdings. It is basically converting all your all your underlying tokens to YT rather than a combination of YT plus PT. So immutable addresses, that's all good. This is the main compound function. We'll come back to this later. An internal function, another public function. Okay, anyone can make this contract to approve the balancer vault to spend any token, basically. So this balancer vault should be like, this balancer vault should be an immutable contract, because this balancer vault can steal all tokens in this contract. So this balancer vault, once this contract is deployed, people should verify that it is set to the right address, and like it can't steal funds from this contract. So that's my number one point. And just to repeat, using this function, you can give the balancer vault permission to spend all your assets. So the balancer vault should be a legit contract which does not spend your funds. I don't have the balancer vault source code here, or else I would have verified if balancer vault can, like, is there any backdoor there or something which can be exploited. This contract actually shouldn't be holding any funds anyway, so this is fine, I guess. This just compounds the tokens and returns you everything. Okay, so the compounding count should be between 0 to 31, not 1 to 255. So your code comment or your code is incorrect. One of these two things. Most likely the comment is incorrect, because if you do it more than 31 times, it will likely just go out of gas. Okay, they have decided to skip permit for now. That's fine. Okay, the smart contract uses transfer. This is just getting the underlying token from base token address. So this is the underlying token I was talking about. This gets the initial balance of the user. Position address, underlying transfer from. So this transfers the underlying token from user to this. It directly sends it to the position address. That's good. This basically starts the deposit function. Will like later be used to start the deposit function in Element. We are sending the underlying token from user to Element. And then eventually, like later on, we'll get yield token and PT from Element, and we'll again sell that PT for underlying. Repeat this process to mint more YT and LT and stuff like that. So yeah, we are doing that in a loop here. I'll enter the loop later, but this loop returns a YT balance amount, so the yield token the user would have gotten. And this ensures that the final result is more than the expected amount user expected. This avoids slippage and the sandwich attacks that I just described in the UBI burner. That's good. And then it transfers that YT balance back to the user. So yeah, this contract does not hold any funds, so all good. And we also verify that the output is more than what the user expects. Okay, so this I'll say is like, it's fine if you are returning this data, but this is just like increasing the gas cost for no real reason. So yeah, just one thing to point out. Now let's enter the loop. One thing I'll say is the indentation. This is not the standard indentation. The Solidity guidelines are present in the docs. They will tell you to indent your code something like this. This does look cleaner, if you ask me. No bug here or whatever. It's just like your guidelines for writing code. You can use the Prettier plugin. It has a Solidity add-on, and that will automatically format your Solidity code. I think it's quite nice and will save you from manually doing all of this. Okay, back to the code. We start with YT balance equal to 0. We start a loop. Here, the same point, uint 8, you can use uint 256 instead and save some gas. uint 256 pre-funded deposit. So since we have already transferred the tokens, we are calling the pre-funded deposit, and the yield and PT token should be sent to this address. YT balance is increased by the YT we get. Then we swap the PT for the underlying asset, I suppose. Yep. So if it is the last loop, if I equal to n minus 1, that's cool. The next loop will be I equal to n, and that will break. So yeah, this is the last loop. Send the remainder to message sender, else send the remainder to this tranche address or wrapped position address, which will help you compound the effect. It's interesting that the wrapped position address is different from tranche. Anyway. Yep, to address. Balancer pool ID. This is hard-coded, I suppose. Oh no, it's provided as user input. Base token address. This is the one you want. Address this. And PT, this is the token you are selling. So everything cool. In this, you are selling your PT and you are getting you are selling your PT, getting the base token, and the base token is directly going to the tranche, where in the second loop you will again create PT and YT out of that base token. So this loop looks fine. This is overall you could do sandwich on balancer, but we don't have an issue here because we have this check. Even if someone tries to do a sandwich on the balancer, this check will eventually fail when the resultant output is less than the expected amount, and we'll be golden. The sandwich attack will be stopped. So I think that is all good. We return the YT balance finally. I'm just verifying that we are only using message sender here, and no other address other than message sender should be able to call these functions. Yep, only message sender can call these, so that is also good. Swap PTs for base token on balances, so we call this. Ooh. So the exact thing I was looking up, I think I found here. This is a public function, and the from address is a user input rather than being uh, rather than being message sender. So this is a problem because as we have seen, the user will be approving the tokens here if they want to use the compound function naturally. Okay, so I have one concern about this contract. Uh, do we have the authors of this contract online? I want to confirm if this is live or not. I don't want to talk any. I don't want to talk more if this is a live contract. I'm looking at the chat if the people are online. This is not an element phi contract. It is created by a third party, but uh, since I'm not sure if this is a live contract or not, I will leave this as it is. But yeah, I think there is a potential bug is in this contract. So anyway, we have covered this contract. This has bugs. This one has bugs. This one does not have bugs, but has some minor improvements. Paywall, I can't remember. Yeah, this has the concern around only owner. No bugs, just one concern. Options LMs has a critical bug. Bridge deposit is a basic contract where you just trust the owner. So no bugs, but you must be trusting the owner. So as you can see, like if you pick any random contract from the internet, you are very likely to find some bugs and some critical bugs in those. Um, and that was it. I think the stream has gone for 2.5 hours. I would look at the chat for a bit. If anyone has any questions or anything, I'll answer those. Stick around for maybe 5 more minutes and then we can call it a day. Meanwhile, I should just message these guys on Twitter if this contract is live. If they come back to me within like a good time frame. Looking at their GitHub repo, doesn't seem like the contract is live. They only have Gorley address in there. But I'm still like, I would wait for like their reply before I talk more about that contract. Okay, I think we can call it a day for there. This contract, I will likely, like once I get a response from the authors, I will probably just post a Twitter comment or something like that describing the bug. Or this actually you guys can take on as a challenge or something. I think I've given enough hints in the call itself to be able to figure out what's wrong with this contract, and like in future you guys can avoid that. Again, I've not 100% verified the bug. I just have a feeling that there is a bug. I don't want to verify it while being live. Okay, thanks everyone. Thank you for coming to my live stream. Honestly, I think it went better than I was expecting for my live first stream. I was totally expecting there to be at least a dozen technical issues or whatever, but maybe YouTube is more mature than I was expecting it to be. This is gonna be the outro. Have a nice day, everyone, and we'll probably talk soon. Cheers. Bye.